Okay, estimating the variance in the error terms. So we want to be able to estimate the common variance. Remember, the idea is we have this picture here that, you know, if we have a point pattern like so, and then we have a regression line, which just happens to be crossing through the origin here. That was an accident. Then the idea is that these errors all have the same normal distribution, right? Okay. With the error terms have mean 0, right? Mean 0 and variance, common variance sigma squared. We want this sigma squared to be as desirable, or to be small as possible. That's going to be desirable because, you see, I'll show you a couple of couple of examples. You know, if in this case, you know, you have it certainly seems that perhaps the sigmas or those variances could be the same, but they look rather large, right? So if I observe an x value down here, then the associated y value, conditioned on the predictor variable being here at x, is not, it's going to be difficult to predict the response variable with any degree of certainty because there's such a large spread outiness, right? So forth. But on the other hand, if we had, something like this, oh, that's really nice, right? Because this sort of says that, that there's a lot less uncertainty in our response given an x value, and that's what you like to see. We like to be able to. We like distributions that are nice and spiky, that are nice and clustered right in around a certain value. Okay, so we can't know the actual variance of those error terms exactly, but we can estimate it with something called the error mean square, or mean square error, MSE. Okay, which we'll take to be just the sum of squared errors divided by n minus 2. So more generally, a mean square, a mean square is a sum of squares that just divided by its degrees of freedom. So it's sort of an average, but you're dividing by the number of degrees of freedom. And the number of degrees of freedom is going to be the number of data points minus the number of model parameters that we're estimating. And that's a sort of a general rule for degrees of freedom. Here we've used we're estimating 2 betas with these two guys here, the beta naught and the beta 1. Okay, so we're estimating 2 quantities, beta naught and beta 1, and so we'll have n minus 2 degrees of freedom. Turns out that under our model assumptions then, that this quantity MSE, this mean squared error, is in fact an unbiased estimator for sigma squared. That is, the expected value of this quantity is sigma squared. So it's a good way to estimate the common variance. Okay. So as an example, if you recall that the output from the ACT versus GPA example, there were 120 observations. You can type this command in row parenthesis data. That'll give the number of rows so that you don't have to just type data and go down to the lowest, go all the way to the end. This will give you the number of observations. And so the degrees of freedom will be 118, 2 less than the total number of observations. The error mean square is also called the residual standard error. Okay, and it was given in the output there. In the R output is 0.6231. Okay, so our best guess for sigma squared is actually this estimate here. Okay, if I take MSE, it's the square of that 0.6231, and our sum of squared errors is going to be then that I could just take that MSE, right, and multiply it by the mean square error and multiply by the degrees of freedom n minus 2. So take that number, multiply by 118, and that'll give me 45.81.